Yes, this meeting is being recorded. Thank you, Zoom. And with that, I will open the floor for Evan. He can better introduce himself as I just did, and then talk about his research, and I'm very excited about it. So I will mute myself as well, and then the floor is yours.
All right, thank you for the introduction, Helena. Can you let me know, Helena, can you see my screen and hear me fine?
Yeah, I can hear you fine, and I see the title slide.
Okay, perfect. Well, yeah, thank you everyone for showing up. I'm really excited about how many people had nothing better to do on a Friday night. And I feel weirdly excited to give a talk at 9 p.m. on a Friday. It's a bit more exciting than the last Friday nights have been. Anyways, today I'll be talking to you about investigating the influences on Thermokarst lake water balances between Nunavik and Tuktoyaktuk Northwest Territories. So this is a part of my ongoing PhD thesis work. Yeah, and it's kind of in the format of a longer conference talk and maybe a bit more of a story about collecting this data and going through the process. So why do we care about lake hydrology? Sorry, there's just a bit of a delay here. So lake hydrology, we can think about as some simple components as water level, the water source, the residence time of the water in the lake, and the timing of ice on and ice off. So these are just kind of some principal components of lake hydrology. And there's a lot of different interactions between lakes and other components of the permafrost environment. So we have evaporation going on from lakes, and the water vapor is, of course, a great greenhouse gas. It's very effective, and the timing of ice on and off and the temperature of the lake affects this. And there's feedbacks with precipitation and air temperature on lake hydrology. So it's this kind of, these two things affect each other. And then of course, both the lake hydrology and regional climate kind of work together to affect permafrost. So we have thaw slumps, which form on the edge of lakes, thermal erosion of lake shores, bringing in permafrost material into the lake and mixing with the lake waters. And we also can have rapid drainage events from lakes. So we have these high lake levels in the summer. They can trigger rapid drainage, which you see in the bottom left-hand corner. And entire lakes can drain away in a day and has very disastrous consequences downstream, especially if there's some infrastructure there. And of course, all these things also combine together to affect greenhouse gas emission and consumption by lakes. So we have carbon and nitrogen and other things being released by thawing permafrost, being taken up by greenhouse gas producers, and kind of forming this permafrost carbon feedback loop. So I'm working on this lake hydrology research from the context of how does lake hydrology and these principles of lake hydrology inform all of these other aspects of the permafrost environment. So that's kind of how I'm kind of approaching these this hydrology from. So the two questions I'll be talking about today are, what is controlling the runoff into these lakes? And I'll focus a lot on snowmelt runoff today. And I'll talk about what is the extent of hydrological variability across the region and how we go about assessing that. So first, a little bit about the study area. You see it in the white box here. It's directly east of the Mackenzie Delta, if you're familiar with that area in the Northwest Territories of Canada. It's within the Inuvialuit and Gwich'in settlement region. It is underlain by continuous permafrost, and there's about 15,000 lakes in this 5,000 kilometer square box. And they're all relatively shallow, 1 to 5 meters deep, and they're only about 18 hectares area on average. So they're all quite small, and they don't really even show up in this image. And as far as climate goes for the region, It's a bit variable. There's more precipitation in the south, but about 50% of it falls as snow in either area. The mean annual air temperature in the south is 2 degrees warmer, so -8 versus -10. In the north area is shrub tundra, so just low shrubs, 1/2 meter tall, maybe 1.5 meters tall, some species. And then the south is boreal forest. That's just about the southern quarter is boreal forest. And yeah, that's a bit of a background on the region. So the question is how do we go about, we have this big 5,000 kilometer square region, how do we go about trying to understand and assess hydrological variability in this area? And the approach I've taken is kind of a multi-scaled study where we have some intensive studies at these 2 lakes you see on the right, Big Bear and Little Bear Lake. And then we also do some regional isotope sampling. And the isotope sampling just gives us small snapshots of hydrology, but it allows us to visit many more lakes so we can get an idea of actual variation. And then the information we're gaining from the detailed studies at these 2 lakes kind of informs how we interpret the isotope data. So I'll talk a bit more about that now. So as I said, we've been doing a water balance at these 2 lakes, so measuring lake level, measuring discharge, measuring the snowpack, storage of water, all these things. And you can see the white line that goes north of each lake represents its catchment, so all the water that's flowing into the lake. And you can calculate a property which will show up in this talk a few times called the lake area catchment area ratio, which is just a way to say how many times larger is the catchment than the lake. So for Big Bear Lake, its catchment is about 6.7 times the size of the lake, the area of the lake. And for Little Bear Lake, the catchment is 84 times the size of the lake. So it just gives you an idea of the relative amount of runoff which can be delivered to the lake. And I'll talk about this more later. And then for the isotope survey, we sampled 20 to 25 lakes 5 times throughout the year. And we sampled them from about a 70-kilometer long transect along a new highway that was built. And we took samples starting before snowmelt and then after snowmelt and all the way until September to get an idea of any sort of yearly changes in lake hydrology. And if you're not familiar with isotopes, I won't go into the methods so much here, but 2 things we can use stable water isotopes to calculate are the evaporation inflow ratio, which is how much water that flows into the lake ends up evaporating. So if this ratio is 1, that means all the water that flows into the lake is being evaporated. The second indicator you can calculate is how much of the lake's volume is replaced by snowmelt. So if we have snowmelt occur, does 50% of the lake get replaced by snowmelt runoff, 10%, 90%? We can calculate this with stable water isotopes. So first I'll talk about the snowmelt response of the lakes. And first, a bit of a background is how does the snowmelt water physically enter the lakes in the first place? So here you can imagine a cross-section of a lake. At the end of winter, we have snow on top of ice, and the ice at the edge of the lake is usually frozen to the bed of the lake, and beneath that we have water. And in this area, just from the lakes I've sampled, on average, about half the depth of the lake is frozen. So the lakes are only 2 meters deep on average, and the ice is 1 meter deep. So the majority of the water in the lake is actually ice at the end of winter. When snowmelt runoff begins to flow onto the lake, it flows onto the periphery of the lake. So here we're looking at a picture of the edge of a lake, and snowmelt water is flowing onto the edge of the lake and ponding just on the edge of the ice. And because the water is bringing heat with it and has a lower albedo, it begins to preferentially melt the ice at the edge of the lake, and the ice might bulge up a little bit. This goes on throughout the snowmelt period, You know, the snow melts off the lake ice, and this moat around the edge of the lake, which is this dark brown water, continues to melt through the lake ice until a point where parts of the lake ice have melted all the way through to the bed or through to the water beneath, and the snowmelt water is able to start mixing with the lake water beneath the ice. So that's what has to happen for the water to actually physically be able to enter into the lake water beneath the ice. So the first question I had was, how much lake water is replaced by snowmelt? So about, in the Arctic, you know, half the precipitation is snow in most areas, more or less. And all the snow melt, you know, is running over these soils, which are just beginning to thaw. The water can't be stored in the soil because it's frozen, so there should be a lot of runoff going to the lakes. And it's all delivered at once. So intuitively, I thought, well, I imagine most of the lake water, or a lot of the lake water, gets replaced by this runoff of snowmelt in spring. Just because of those conditions. It's half the precipitation and it's flowing over the soil. And what I found with this isotope data is that on the right here you see for 20 lakes, the percentage of lake volume replaced by snowmelt from that regional isotope survey. And on average, it was only 17% of the lake volume had been replaced by snowmelt runoff. And that seemed really low, because it's just as a function of the amount of snow that's on the land compared to the amount of snow that ends up staying in the lake, it's a small fraction. So that really surprised me. Another interesting relationship that came out, which is on the left-hand side here, is the amount of snowmelt runoff that remained in a lake was higher if the lakes were shallower, and as a consequence, less of the lake had been frozen. So on this graph on the left, we have, on the left-hand side of the graph, we have lakes with higher snowmelt dilution. Most of these lakes had most of their water volume frozen because they were shallow. They were only 1 or 2 meters deep. Whereas on the other side of the graph, we have lakes which are 3, 4 meters deep. So they had much more liquid water in them at the end of winter. Less of it was lake ice, and they had much less snowmelt dilution. I couldn't really figure out this relationship at first. It didn't make sense. And at the same time, I had this question. So we looked at that process of how the ice has to melt for snowmelt water to enter the lakes. And I wondered when that timing happened. And I thought maybe the water was running onto the ice, creating this moat, and it was flowing over top of the ice and out of the lake before it had a chance to mix with the water beneath the ice. So maybe the snowmelt came onto the ice, flowed to the lake, out of the lake, and that's why there wasn't so much snowmelt runoff left in the lake, because it had just flown over the ice before it had a chance to actually mix. So to answer this question, I took isotope samples of the lake throughout the snowmelt period at Big Bear and Little Bear Lake, those 2 lakes I had shown earlier. And so I was taking an isotope sample through the ice in the center of the lake, and I was also taking an isotope sample of the water flowing out of the lake. And I assume that if the snowmelt runoff is mixing with the lake water, I'll see the lake water start to become more like snowmelt runoff. And the water coming out of the lake should match the water that's in the lake. So first, the isotope data is just on these top 2 graphs here. You don't have to worry about the numbers, but just look at the y-axis of the top graphs here. So on the top of the y-axis is lake ice. So this is the isotopic composition of the lake if all the ice was going to melt and no snowmelt water was in it. And the isotopic composition of the snow is much more depleted, so it's at the bottom half. So you can use these 2 things as a reference. And the circles here represent the lake water, and the squares represent the water that was flowing out of the lake outlet at the same time. And then this is through time. The date is just transposed to the bottom here. So from the beginning of the snowmelt period up until this red line, the isotopic signature of the lake wasn't going towards the isotopic signature of the snow, it was going towards the signature of the lake ice. While at the same time, the isotopic signature of the water flowing out of the lake was much more snow-like, and it was going towards the signature of the snow. So that's telling us that for the first 7 days of the snowmelt runoff period, there isn't actually any snowmelt runoff making it into the lake water beneath the ice. And then sometime between this red line and this blue line, the isotopic signature of the lake shifts very rapidly towards the signature of snow, and it becomes more like the signature of the outflow. It's even more extreme in this case for Little Bear Lake, where the signature of the outflow and the lake are identical on this blue line on May 25th. So in between those 2 points is when the lake water started to mix with the snowmelt runoff. So I wondered, okay, how much water has gone into the lake before this point? Because I want to check if could a lot of this lake water flowed out of the lake over top of the ice, and that's why we have these low snowmelt dilution values. But Little Bear Lake, if we go to the bottom 2 graphs here, this is the lake level for the same time periods. That Little Bear Lake, you see lake level rises very rapidly because its catchment is so much larger relative to its size. And that steep decline in lake level is, there's a dam of snow at the edge of the lake which fails, and it lets all the water out. So that snow dam was burst much more early at Little Bear Lake than it was at Big Bear Lake. And at Big Bear Lake, the snow dam didn't burst till much later, and as a consequence, there was very little water flowing out of the lake during this whole time. So we didn't have discharge measurements, unfortunately, but just from observation, it was just a trickle of water coming out of the lake. So we can calculate how much water flowed into the lake from the start of the snowmelt period until we saw the snowmelt starting to mix with the lake water beneath the ice. And at Little Bear Lake, that only turned out to be 5 to 8% of the snowpack. So it was very little water that had the potential to flow out of the lake, and that water didn't end up flowing out of the lake because it was blocked by this dam of snow. So that whole hypothesis about water flowing over the ice was wrong, and I had to look a bit deeper to see why we were getting these low values and look more into the literature. So the next step I took was I wanted to look at what is related with snowmelt dilution. So here's just a table of a linear correlation between the amount of snowmelt dilution and some lake and catchment properties I had for these lakes. And interestingly, I had always assumed too that if a lake has a bigger catchment relative to its size, so this lake area divided by catchment area, if a lake has a bigger catchment, it will have more snow in that catchment and more snowmelt will be delivered to that lake. And I would assume that there would be more snowmelt left in the lake just because there's more snow being delivered to it. But there's no correlation with that either. If a lake had a big catchment or a small catchment, it didn't matter. It didn't affect the amount of snowmelt runoff that was left in the lake by the end of the snowmelt period. So I dug further in the literature and I found that the reason is probably there's a process of density stratification in the lake, where the water flowing into the lake is near 0 degrees, and then it flows under the ice, and it starts to come into contact with the lake water. Now the lake water is relatively warmer and closer to 4 degrees, which is the densest part or the densest temperature of water. So that snowmelt runoff flows under the ice, and it doesn't mix with the other lake water because there's no wind to help it mix because it's covered by ice, and then it flows out of the lake. So that was the reason why there wasn't any, I was looking at these things from a hydrological perspective when I needed to start to take into account things like density and a bit of limnology to understand why I was getting these results. So that was, yeah, that was an interesting experience. But the consequences is you still see there's a whole bunch of water being delivered to these lakes. You know, they're not at a, it's not like the snowmelt isn't getting to them. Still hydrologically, they're getting a lot of water, but it's not actually remaining in the lakes. So it's two different tales. One, hydrology, there's a lot of snowmelt, but limnologically, there isn't much snowmelt in the lakes. Now I'll move on to summertime hydrology. And for isotopes, we can calculate, I said before, the ratio of evaporation to inflow. So how much of the water that flows into a lake ends up evaporating. And again, we had there's a very strong correlation between the ratio, the lake area catchment area ratio, and the amount of evaporation. So what this graph is showing is lakes which have relatively small catchments end up having more of their water evaporate. And a corollary of that is that they have a longer residence time. So lakes which have larger catchments have less of their water evaporate, and most of it just flows out of the lake. So, and this makes sense if we go back to look at our water balance, the two lakes where we're doing a water balance. For a rain event of 25 millimeters in the summer, this is just one I picked out, the rise in lake level at this Little Bear Lake was much more than at Big Bear Lake, but the volume of water delivered to the lakes was roughly the same and more or less a proportion of the size of their catchment, which makes sense. But when then you look at the volume of water which was replaced by that rainfall event, there was only 1% of the lake volume which was replaced by rainfall runoff for Big Bear, but 17% of the lake was replaced by rainfall runoff for Little Bear. So it's like the same amount of water is being delivered to these lakes because their catchments are roughly the same, but the consequences are very different for the residence time and the lake level because of the size of the lakes. So the next step is to take this isotope data, and I've just shown you one correlation here, but apply some more statistics to see how things like vegetation and the connectivity of the streams within the lake catchments and all these other properties correlate with indicators we can calculate from isotopes, things like evaporation inflow or snowmelt dilution, and then see if we can upscale that to the larger region, just to get a sense of the variability in hydrology among these lakes. Because there's still 15,000 lakes and we've only sampled 20 or 25. So as I was saying, there's many remote sensing data sets now that we can do this with. Arctic DEM is one of them. And another one is this vegetation height product, which is at the 20-meter scale, which we can use to extract vegetation height from the catchments and see how it correlates with aspects of lake hydrology. Another thing this allows us to do is see how representative the field sites we're looking at intensively are of the greater region. So this plot here just shows lake surface area versus lake catchment area, and the darker areas are more common features. So this is for all 15,000 lakes in this region. And you see Big Bear Lake falls right within the dark region, saying that it's a pretty common proportion of lake for this region. But Little Bear Lake is starting to fall towards the kind of less common type of lake for this particular variable. So the three take-home messages are the snowmelt recharge of lakes is relatively low, but it's also variable and depends on the depth of the lake. The relative size of a lake catchment is the main control on evaporation inflow, the variability in lake level, and the residence time of the lake. And pairing these water balance studies with regional isotope sampling is quite an efficient way to get a good assessment of a region's hydrology. And thank you all for listening.